Hello everyone, my name is Jordan Hernandez and today I'll be going over Demo 7. So Demo 7 today is going to be split up into two different parts. So part 1 is going to be about my ALU and the second part is going to be about the microprocessor. So today we're going to be going over the ALU. So learning targets to think about in Demo 7. So 10B is I can describe the interactions between control and data path circuitry. 11A, I can apply registered transfers logic to design sequential circuits for basic applications. And the 11B is I can demonstrate the operations of microprocessors, memory, data path, and control. So here's our problem today. So back all the way into our class, we were given a microprocessor on day 1. And with that, we have the ALU Mini, which is a separate owned circuit to represent like a multifunctional operation calculator. So as we can see here, it has about 4 different modes, which is subtract a minus b, add a plus b, multiplication ls4, and multiplication ms4. So as we can see right here, this is what it will look like inside of the microprocessor. And yes. And as you can see, we have the values A and B and our selection, which is 0, 1 and 0 and S1, or S0, S1. And what we're going to do is that we're going to add more into this. So our first one is we're going to add 4 new operations, and it could be shift right or bitwise XOR. We're going to add a selection number 2 or S2. So that we can have, since we're going to have about 8 different types of modes, that we can have up to 8 selections in total. And we're going to expand the muxes since we're adding more to S2. And I'm going to write down some notes for not only for myself but other people to understand what each type of mode is going to be about. So as I can see here, what I chose for the new operations. So our first one's going to be bitwise OR, bitwise XOR, bitwise AND, and bitwise NOR. And here's what they're going to be looking like for each of those circuits. As we can see, we have this guy with the OR gate, this one with the XOR gate, this one with the AND gate, and this one for the NOR gate. And they kind of link up with each other over here. So, as related back to my previous ALU, I call this one the updated ALU, as this is my version of what the expanded of it's going to look like. So here's what's going to look like. As we can see here, we have this eight different modes: subtract, addition, multiplication, ls4, and multiplication ms4 for 3, 4 for bitwise OR, 5 for bitwise XOR, and 6 for bitwise and 7 for bitwise NOR. As we can see here, they're all right here at the bottom. And then as you can see, this is a little bit similar back to the older design, since I was able to add more stuff at the bottom. I made the selections right over here to kind of make it easier to understand how to input them. So, without all ado, we shall go to our test circuit. So here it is right here. So I'm just going to turn these guys off for now. But yeah. But as we can see here, my bitwise OR, bitwise XOR, and bitwise AND, and bitwise NOR. And I made them the appearance of logistic holy cross. So when I was able to put them out, they're going to look like this. As we can see, I'll put one out. Yeah, right here. So I was able to pull those guys out to represent those types of equations for whenever A and B is for my total. So for this test, we're going to be doing 0, 1, 0, 1, which is going to be 5 for A. And then this one's just going to be 1 for B, which is 1. And we're going to be going through all the different types of operations and which one's which. So, let me go to auto real quick to kind of have everything on the screen. As we can see here, our final equation when it's subtraction is 0, 1, 0, 0, which is 4. As basic, 5 minus 1, which is 4. Yep. And then for selection 1, 0, 1, 1, 0, which is 6 for an addition problem. For multiplication, ls4, we have 0, 1, 0, 1, which is basically 5. And then when we move on to 3, it's going to be 0, 0, 0, as it's going to be the most significant bit in 4. For XOR, we're actually going to move it to mode 4, which is 0, 1, 0, 1, which is basically our 8 or 5. XOR, it's just basically going to be 0, 1, 0, 0, which is technically 4. Yes. Then when we move on to our mode and, we're going to, which is 6, it's going to be 0, 0, 0, 1, as we can see here. Yeah, right here. And the reason why this is kind of showing that is that whenever both, because each time when you implement to each one, so like let's say I have 1 and 1 right here on just A0 and B0, it's just going to output as 1. So in order for it to output, they both need to be the same. As we can see here on my updated ALU, we only have these two being the same, so it'll output just that. So for NOR, this one is actually just going to be the opposite of OR, which was my 5. So that when it outputs, which is 5 is 0, 1, 0, 1, as you can see right here, it's going to output as 1, 0, 1, 0, which is going to be -5 in sign. And C. And the reason why it's useful to have the multiple functional calculator inside the center of the microprocessor is that if we were to have all of this stuff into the microprocessor, it's gonna, one, look a little bit more complicated to kind of add all that stuff into one microprocessor, and 2, it's easier to kind of have it all in one, so that we're not gonna have maybe about, because if we were to have all 7 of these, it would just be, or if we were to have all 8 of these, it's just gonna have 8 microprocessors, which is way more complicated and more time to make, rather than just kind of have it all in one, which is, yeah, it's going to have a lot of work, but it's going to be easier to basically have it there, so that we're not going to have 8 different microprocessors to worry about just for one simple equation to do. And I believe that's going to be it for today. The next video would be about part 2. I hope you guys all enjoy, and I'll see you all next time.